Hi there everyone, welcome back to a new video in which we will be reviewing an interesting paper titled On the Dynamics of Inference and Learning. This paper was authored by David S. Berman from Queen Mary University of London, Jonathan J. Heckman from UPenn, and Mark Klinger from University of Illinois. Throughout this summer, I have been involved as a research assistant or research engineer under the supervision of David Berman, trying to develop a software that proves the theoretical results regarding neural networks. The theoretical results coming from this paper, I thought they were quite interesting, and as well, I think they meet the criteria of using physics, theoretical physics more specifically, in the field of, in this case, statistical learning or even deep learning, applications in deep learning. Okay, so I just realized that putting the paper horizontally would be better for the video actually, so let's just do that. But yeah, coming down to the abstract, here, as it says, statistical inference is the process of determining a probability distribution over the space of parameters of a model given a data set. As more data becomes available, this probability distribution becomes updated via the application of Bayes' theorem. This is how, basically inference is thought of, how it's described. But in this paper, we're gonna, look at this process and treat it more specifically as a continuous dynamical system. It's a novel way, and that's the whole point of this paper. And this paper basically proposes a novel treatment of this process, the process of inference as a continuous dynamical system. And actually, in later sections, the authors will derive a first-order differential equation that describes a trajectory or a flow in the information geometry that only depends on the model used. And actually, for some specific situations, more specifically when the Kramer-Rao bound is saturated, we won't get too deep into that in this video for sake of length, pretty much. When the Kramer-Rao bound is saturated, we can actually solve this differential equation and get a solution that seems to be a power law, a simple power law of 1 over t, actually. Where t is actually a time-like variable, but in this case, it denotes the quantity of data. And the authors as well, to prove this point, they used both analytic and numerical examples using Gaussian random processes where inference is involved. They also used the 1D Ising model, a model that is quite famous and it's solved as well. And then the more interesting part to us is that they also evaluate the qualitative behavior exhibited by Bayesian flows to the training of various neural networks on benchmark datasets like MNIST or Cypher10, whatever. We will get deeper into this later this video, but we're gonna be assuming that neural networks use inference. They basically try to follow a coherent way of coming up with the appropriate weights and biases, and therefore we should assume that this differential equation that describes flow also applies to neural networks. All right, so in terms of the contents of the paper, I think it's worth clarifying that we're not going to go through the whole paper. As you can see, it's 32 pages actually of paper, so for sake, simply so I don't do an hour-long video, we're gonna try to just focus on some bits which I think are the most relevant for this video, or for the purpose of this video at least. So we're gonna go through the introduction. We're gonna go through the first point in section 2, so we're not gonna dive into whatever there is between 2.1 and 2.7. Although if you find the paper interesting, whatever we go through today, I would recommend it, hardly recommend it, because especially 2.5, well, of course you're gonna have to learn all the mathematical derivations between 2.1 and 2.4, but yeah, 2.5, 2.6 and 2.7 are actually quite exciting. And this is the reason for that explains the results really, like that follow up on this work. Then as well, because we're gonna try to focus more on the deep learning side of the paper, we're not gonna get into the Ising model or the dynamical base for Gaussian data. And we're gonna jump straight into section 5, and then we'll have a look as well at the section of conclusions and discussions. Okay, so starting off in the introduction, and because we're gonna be discussing topics in statistical learning in a Bayesian setting, we have to, and we must pretty much review what the Bayes rule is. And we can see it here in all its beauty in equation 1.1, and it basically says that the probability of A given B is going to be equal to the probability of B given A times the probability of A all over the probability of B. Here we call the probability of A given B, we call it a posterior, and then the probability of B given A would be prior, right? And if we assume, we're going to use this equation to pretty much define our inference scheme. And if we assume that we have a continuous flow of new evidence or new data, then we can treat the previous posterior as the new prior, and then pretty much learn in this way, right? In fact, we can see situations like this all around the field of physics. Here the authors actually give a few examples. For example, in quantum field theory, one often is interested in particle excitations where the structure of locality is built into the inference scheme. In this context, new evidence amounts to proving shorter distance scales with the help of a higher energy collider experiment or a more precise measurement of a coupling constant. As well, they mention that how they deal with it in modern terms, as they mention here, it's using the renormalization group. This renormalization group, it's pretty much a method used to look at the changes in a physical system on different scales. As well as they mention down here, let me just find it. Oh yeah, here it is. Basically, in this paragraph, right? Basically, the essential idea is that the inference process converges towards a best guess, right? That is the idea, and therefore we can spot a similarity there with the diffusion equation. Which is, what I mean by the diffusion equation and what they mean is the thing that describes the macroscopic behavior of tons of microparticles in Brownian motion, actually. But starting with the Kullback-Leibler divergence, I never know if I'm pronouncing that right, actually, which we're just gonna call KL divergence from now on. And it comes derived here. The KL divergence is simply a function that measures the distance between two distributions. Then we have a set of fitting parameters, right, that we're gonna try to update in each of the steps of the inference schema, and we're gonna update it in this fashion. So our model is just gonna have the observables given the parameters, and then we're just gonna, the parameters at one point are theta k, and we're gonna update them to theta k plus 1. And we are gonna assume, or we should believe, that there is a theta k, or this whole process is gonna converge to a theta k that is actually gonna be an optimal theta for which the distributions are gonna be the same. So m of x is gonna be equal to t of x. Here again, we can see how this optimization process, we can picture it as a, for example, a kind of bumpy mesh, right? A 3D mesh. I'm just picturing. My drawing skills are not the best, so I'm just doing a 2D sketch of this, and we can think about a ball looking for the minimum, right? That's how optimization is. There are kind of little local minimums here, but we're ultimately looking for this point, right, at which the loss or the KL divergence will be at its minimum. So yeah, basically we're here minimizing for the divergence. But in any case, what I wanted to get to with this drawing is that this is how we can imagine the learning process, but this mesh is going to be described as the by the information geometry, and yeah, we're trying to look for an equation that describes the trajectory that it takes for the particle to get to this minimum here, right? And if we continue reading the paper, it mentions here how in Bayesian inference we treat the parameters theta as random variables as well, and these are dictated by a posterior distribution pi of theta and t, which updates as a function of the data steps t. And then for any observable O that depends on these parameters, then the appearance of this in various averages results in an implicit time dependence and a corresponding flow equation, which is ultimately what we're looking after. And we can see it here in equation 1.3, where here this line on top of the observable means the average, and this here is going to be the variance between the observable, and then this D is basically going to be the KL divergence, so the distance between the true distribution and the basically what we're getting, the results, the distribution we're getting at that specific time step in the inference scheme. And yeah, here as well, if one has some background in not particle physics but theoretical physics, then we can spot again here a striking formal resemblance between the evolution of the parameters of these models of theta and then the evolution of parameters in renormalization groups. In the renormalization group flow. And yeah, continuing here, we get introduced again that for specific situations, so whenever the Cramer-Rao bound is saturated, then we can solve the equation exactly, the flow equation. And yeah, as they mentioned here, this yields to a simple 1/t power law scaling. And yeah, we can also introduce hidden variables, for example, and yeah, they're gonna change things a little bit, but again, we're not gonna get too deep into that. But yeah, let's continue in here as well. Here's a pretty important part of the introduction section related to neural networks, and yeah, I mean, it is also natural to ask whether we can apply these considerations even when we do not have a generative model for a probability distribution, right? That's a pretty normal question. And then from the Bayesian perspective, neural networks are models that contain a large number of parameters given by the weights and biases of the network, and training is a flow on those weights and biases induced by the training dataset. So this is the important bit, right? Like, Again, neural networks have a bunch of parameters that are basically the weights and biases, and depending on the complexity of the neural networks, they can have billions, and therefore it's not gonna be possible to carry out like a quantitative analysis, right? Because it's just impossible. It's not like, for example, like the Bayesian model. That's why they're touching on it right now, because it's possible to do it by hand, kind of thing. But yeah, because they assume again that neural networks engage in rational inference, then there is not really a reason for which we should think that the flow equation shouldn't hold, right? So flow equation, we should expect it to hold. And yeah, like what I was personally working on in this project more specifically is studying the phenomenology of training a network as a function of the size of the dataset. And I will link actually the GitHub repo that I'm working on in the description, so you can have a look. It's quite interesting actually, and kind of like a funny thing to do and play around. But yeah, we used feed-forward networks, convolutional neural networks, and some state-of-the-art networks such as ResNet and EfficientNet as well. We're trying to get some results with those on more like benchmarked datasets like MNIST, Fashion MNIST, CIFAR10, etc. And yeah, the good thing is that quite remarkably, we find that the behavior of these networks are generally following the 1/t power law behavior solution that they derive mathematically. Okay, so getting to section 2, this is actually where it gets interesting. We're going to present, or the authors are going to present a physical interpretation of Bayes' rule as a dynamical system. And how do they do it? Well, it's quite a nice mathematical derivation. And they work in the limit where they assume to have a large number of events. So, not this. Let me just highlight it. Okay, so n, where n is the number of events, is much bigger than 1. And it's partitioned up into smaller number of events, so nk, such that nk is still bigger than 1, and but much less than n. And yeah, basically they're gonna show that this system can be expressed with an integro-differential equation. Okay, so we have to assume a few things here. Okay, so we have a set of events, E, that are partitioned again. So there is E1, E2, etc. up until En, and they are drawn from a true distribution. And because we're in a Bayesian setting, we're going to assume that we have a model of the world. We're going to call it f of theta given the observed events, where theta are the fitting parameters, and there are m of them. And basically the density for the data conditional on theta is specified as this. Basically the events given theta. We are also going to assume that there is a specific value for theta, an optimal value for theta that is alpha star, for which we realize the true distribution. So basically the distribution of our model or our model of the world is going to be the same as the true distribution from which E was drawn. As well, because we're working in a Bayesian setting, our update is gonna mean that additional hyperparameters for the posterior distribution pi are being updated as a function of increased data. And therefore, we're going to be getting better and better in kind of approximating this posterior distribution. And okay, so let's actually assume that the observed events are conditionally independent. So if they are conditionally independent, then the posterior distribution is going to be proportional to the conjugate kind of thing. So basically the density for the data conditional on theta, so the events given theta times the prior. And this is only going to be proportional given that the posterior distribution is properly normalized, and therefore that's one thing that we're going to require. And yeah, we can also introduce another distribution from equation 2.1, and we basically want to get rid of the dependency of theta, right? And therefore, to do this, we're going to have to integrate over the space of the parameters, so over the theta, and we're going to integrate this last bit here in order to, basically, as I was saying, getting rid of theta. And then we're just simply going to rearrange and write it in this form. And yeah, we can partition our data again, our events, into even smaller batches. So k, we're gonna call them E in terms of k. So there's gonna be E1k, E2k, whatever, and where k is gonna run from 1 to k, and all of the events added up in terms of k is gonna give n. And this is gonna introduce a cumulative set of events that is described as this, is union, because we're just partitioning. And we can rewrite equation 2.3 in terms of k to see what I'm just gonna talk about now more clearly. In fact, this is a recursion relation because a recurrence relation is simply an equation according to which the nth term of the sequence is dependent on the previous terms. So as we can see here, we have pi of k plus 1, and it's going to be dependent on pi of k. So because there is a recursion relation, this also means that it is a discrete dynamical system. Discrete because in the end we have a discrete set or a discrete interval of k's. Coming up with the unsides for pi k as the exponent of a function lk in terms of theta, and then taking the logarithm in both sides here, we can simply leave this as a finite difference equation. So this is a finite difference equation because it's just a subtraction there and then a logarithm of the right hand side from the previous equation. And okay, so to proceed, they make a few technical assumptions that are important to kind of understand what's going on. Firstly, it's that each draw from the true distribution is independent, and therefore so the total distribution can be split into a multiplication of all of the individual events. And then they also assume that the true distribution can be always viewed as part of the same parametric family as these densities, right? Where E belongs to the set of events k plus 1. And here alpha k would be the most likely estimate of theta given the data. So introducing these terms into equation 2.6, then we get the same difference in the left-hand side, and therefore just a sum of logarithms, right? Because we're, again, assuming this thing here, but because we're working with logarithms, then it becomes a summation. And then we can say that this is the same as the average of all of the logarithms times the number of events, so nk plus 1. And we're basically here substituting, if you notice here, we're substituting E by its continuous analogous. So y is a continuous function because we're in the limit where n and the number of events is really large. So again, they're going to show now that in the limit of n much bigger than nk and much bigger than 1, the Bayesian updating is well approximated by an integro-differential flow equation, which is the whole point of the paper, right? That's why we're going through this section. And, again, because there is a large nk, this means that we can approximate this equation before, so 2.9 or this, the summations basically, by an integral. So we're going to have, again, the same kind of difference in the left-hand side, and then just a summation, an integral over the y space, where y is the continuous analogous of all of the events E. Then each of the integrals here, because this is adding a lot of the same terms. If we remember and we go back to the equation of the KL divergence, then we can see that we can substitute this and express it in terms of these functions. So the difference is going to be just the multiplication, the n stays there, and then it's a difference of KL divergences. So this would be the estimate of the parameter theta, and this would be the actual parameter theta. And here as well, because the difference is infinitesimally small, because we said that we're working in the limit where nk over n is much less than 1, then we can replace the left-hand side and approximate it as a differential equation, or as a derivative, sorry. So for this, we introduce a continuous parameter tau between 0 and 1, which we can partition up into discretized values tau k with a small time step, so delta tau, okay? And so basically they're gonna be described with this equation. So tau k is just gonna be 1 over n over this. So 1 over n times, all of the, n1 plus n2 all the way up to nk. That should be n technically, right? And then delta k is just gonna be the ratio between nk and n1. And n. So but continuing. We can, because we have defined this, then we can talk about the family of distributions, of the prior distributions theta k, as a continuously evolving family of distributions, from now on called pi, without the case index. And then, they write theta of tau to indicate the continuous evolution used in the parameter. And therefore, rewriting this, it can be approximated as the following equation, 2.13, where we're introducing here these differentials that we were talking about, where L is just the differential of L with respect to this new time parameter that we included, that is tau. So it's reflected here. And working in this approximation, so n is a big number, then this is given to the leading order, but by the following equation. So 1 over n, this is simply the partial derivative with respect to the time step, right? And then they just simplify the notation by just writing, substituting what it's inside of the KL divergences by simply like the right parameter, because we're always taking into account the most optimal parameter alpha. And then, as they well said here, we observe that the nk dependence has actually dropped out from the right-hand side, and because if we remember well, it used to be there. Here it is. And this is now only depending on the total number of events, n. So if we put it in terms of the posterior distribution, pi theta tau, again the exponent of L, then we will have this differential equation here. So just the differential of pi with respect to tau, and that's just going to be simply n times the distribution, the posterior distribution pi, times the difference of the KL divergences. And yeah, formal solution is then this equation here, which is an integro-differential equation, as we can see here and here. So yeah, this is actually quite interesting, and this is what it's showing, that we can show this schema, this Bayesian update schema or scheme as a continuous dynamical system. So because the video is already a bit too long, we're gonna skip all of the sections in between, although I really recommend them for you to read. I will leave the paper link in the description as well for that. But yeah, we're gonna straight up jump into the section on neural networks and learning, and then we're gonna discuss a little bit of the conclusions and discussions as well. So yeah, I mean, they took the viewpoint that neural networks are simply a model whose parameters are given by its weights and biases, right? But yeah, I mean, the training of neural networks is a Bayesian problem of inferring a posterior distribution over the weights given by the data available, and then one chooses a net with the most likely weights from the posterior distribution, right? So here we don't have anything to say or anything to kind of argue that this shouldn't follow the flow equation, and therefore they investigated this. They decided to see if this power law was also happening for these complex systems that neural networks are. They empirically investigate whether the neural network follows a similar qualitative dependence on the data as indicated by the dynamical Bayesian updating. In fact, they, as I mentioned before, they were not able to do it quantitatively, of course, because of the large amount of parameters, but they were able to do it quantitatively for the systems like the Bayesian model, and they got really nice results there. That's why I suggest you to read it. If you have understood everything so far, I think you shouldn't have much of a problem to understand the rest. And then, yeah, they expect a simple power law, again, behavior as we approach a high level of accuracy. And they expect also that the loss function exhibits an exponential decay or decaying profile when the inference is only moderately successful. So power law when the accuracy is really high, and an exponential kind of graph when the inference is only, or the accuracy is only moderately successful. Then, just skipping everything like the details and stuff, I will again leave you the GitHub so you can have a bit more a deeper look into the specific networks that we use and the data sets. And we're gonna skip to this part where they mentioned that they wish to investigate the dependence of the loss on the amount of data and not the amount of training of the network. So they have to kind of not keep the epochs constant, but kind of the ratio epochs to data has to be constant. Otherwise, yeah, you will all be you cannot train the same amount for less or more data. Otherwise, it wouldn't be kind of a fair comparison. Neural networks often learn by repeated training using the same data set over many epochs, but they are interested in the final state of the neural network after they have completed training. In fact, we wish to keep the amount of training fixed and only compare the loss with different amounts of data used to training. This is what I was just mentioning now. And to do that, they link the number of epochs to the size of a training set. They just simply create a ratio and keep it constant for all of the training iterations. And yeah, a really important distinction is that if you're familiar with stochastic and Bayes gradient descent, it may feel that they are just doing the same thing in this experiment, and these are just traditional learning curves. But if you think this, you should take a look at the axis of the graphs that we're evaluating, because this is not the case, as they train for multiple epochs and the curves measure only the loss as a function of the total data, not like epochs or something like this. And yeah, I mean, the conclusion of this, I'm not going to show you the results one by one. You can have a look at that and see the numbers exactly. But the conclusion of this is that, after performing multiple trials, we also extract the mean and variance for these fitting parameters. In particular, the exponent appear in the power law fit. We also quote that the root mean variance as an indicator of robustness for the results. And yeah, as we mentioned in the abstract or introduction, we can see, let's actually take a look at the graphs. We can see how they comply these exponentials or power laws for different trials. You can have a deeper look into this. And then we're gonna come down to the conclusion section and discussions. I think this is quite interesting, actually. I'm not gonna repeat myself here. They are repeating how whenever there is the bounds, the Kramer bound is saturated, they get a simple 1/t power law. And yeah, this is actually an analog of the unitary bounding conformal field theory. And this is one of the points where theoretical physics meets this paper. And yeah, what else they mentioned here? Yeah, they mentioned here that they find remarkable that simple Bayesian considerations accurately capture the asymptotic behavior of so many phenomena. And this is true because, again, all of the experiments they have been running are quite different, but in all of them inference is involved, and all of them seem to capture this predicted behavior. And yeah, this is actually interesting. Here they are comparing this to physics, as they say. The appearance of a 1/t to the power of b power law scaling for learning in neural networks is of course quite suggestive. In the context of statistical field theory, the onset of such scaling law behavior is not usually clear indication of a phase transition. Pay attention to this because in my opinion, it's quite cool. We have also seen that inference in the presence of hidden variables provides a simple qualitative explanation for some of this behavior. Although we haven't looked into the details of hidden variables, you can have a look into that as well. It's in section 2. Then here again, they come back to the concept of renormalization group. They mentioned that a unifying thread of this work has centered on a physical interpretation of Bayesian updating. This equation shares a number of common features with the related question of renormalization group flow in QFT. But whereas renormalization is usually interpreted as a flow from the ultraviolet to the infrared, wherein we lose information about microscopic physics, the Bayesian updating procedure does precisely the opposite. They are gaining information as we evolve along the flow. And this is interesting, because they have also taken some preliminary steps in developing a path integral interpretation of a Bayesian flows in the Appendix A. And it actually turns, this suggests that there should be a direct, or basically the motivation of doing this appendix is that there should be a direct analog of Polchinski exact renormalization group equation, which would be exciting to develop. Again, this is in Appendix A. You can find it here. It's quite interesting. I took a look at it. But yeah, coming back to the motivation, and this is one of the things that excited me the most about the paper, is that the motivations are completely disconnected from, seemingly completely disconnected from neural networks. As in fact, they mentioned here, let me just change the color to see it more clearly. One of the original motivations of this work was to better understand the sense in which the structure of quantum gravity might emerge from an observer performing local measurements in their immediate vicinity. From this perspective, each new piece of data corresponds to this local observer making larger excursions in the spacetime, as well as the parameters of the theory. This is particularly well motivated in the specific context of ADS-CFT correspondence, where the radial direction of the bulk anti-de Sitter space serves as a renormalization scale in the CFT with a cutoff. Given that we have a flow equation and that it shares many formal similarities to an RG equation, this suggests that a natural starting point for directly visualizing radial evolution in terms of such an inference procedure, which is amazing. And we can see how this behavior also applies to neural networks. But yeah, the video is already quite long, I believe. If you have any questions on the derivation that we went through or anything at all, please let me know in the comments. We will we can discuss it, or if you want to, if you want me to dig deeper into any of the sections that I had to unfortunately skip, just let me know as well. I will do it with all my pleasure. Thanks for watching the video. If you have gotten to this point, it means that you really enjoyed it. Thanks for that, and yeah, see you in the next one.